Hey guys, and welcome back. And today we're going to be talking about irrational numbers. We're going to think about the word irrational, the root of the word irrational, and distinguish it between the word rational. Okay, so we're going to classify numbers as rational or irrational. I want you guys to think of the word irrational as being the same thing as not rational. We talked about what the word rational meant. That meant that you could write it in fraction form. Whether it starts in fraction form or you are capable of changing into fraction form, that's what rational means. So if something's not rational, that means that you cannot change it into a fraction. So to be successful at identifying whether something is rational or irrational, we're going to need to identify the types of decimals. We're going to need to identify a fraction or a ratio in different forms. And then we're going to be able to tell the difference between the two. So let's take a look at the intro to example 1. It says a number that is the square of an integer is a perfect square. Now I'm going to make a little side note that the word square, the word square, sorry, that's supposed to be an S, is equal to raising something to a power of 2. Okay, the reason why we call it a square is because it's like timesing something by itself, which if you think about a geometric square, if you're thinking about the area of a square, well, area is equal to length times width. Well, the length is the same as the width. So if we call length S and we call width S, that's like saying that area is equal to side times side. That's what I mean by S, is the side length times the side length, which is just side squared. Okay, or side to the second power. So whenever we have the area of a square, an actual geometric square, it's like we take one of its side lengths, S, and we multiply it by itself, because all of these are going to be the same length. So here's the length, here's the width. Really, that's S times S, which is S squared. So all I really want you to take away from that is the word square means that we're raising something to the second power, or we're multiplying it by itself. To be a perfect square, a number that is a perfect square, is a number where it is obtained by multiplying a whole number by itself, which introduces us to the function of a square root. Okay, square root. I want you to write down that this is the inverse of squaring. So just like subtraction is the opposite of addition and multiplication is the opposite of division, square rooting something is the opposite of squaring something. The square root of a number is another number that when multiplied by itself is equal to the original number. Some square roots are rational numbers. Okay, so some square roots are rational and some are irrational. In order to identify whether a number is an irrational number, it cannot be written in fraction form. Well, anything that is irrational is going to be the square root of a non-perfect square. Okay, and we're going to make a list of what perfect squares are, and then we can identify which ones are not perfect squares. Okay, and the square root symbol kind of looks like a division symbol with a tail. Okay, and we need to make sure we understand the difference between a square root symbol and a division symbol. So here I see the square root of 25. So what that is really asking is what multiplied by itself is 25. That's what this is really saying right here. What multiplied by itself is 25, which the answer is 5. So that's what square rooting really means. What multiplied by itself is the number underneath the what we call the radical symbol. Okay, so to continue this introductory to the first example is just more concrete proof of what is happening with the square root symbol. It says a number is a square root of a number if a number a, b, if a squared equals b. So for any whole number that is a perfect square, square root of b is rational. So if I were to make a list before I look at this example, I'm going to square the numbers 1 through 10. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared. Now really this just means we're multiplying it by itself. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, 64, 81, and 100. All of the numbers in this column, those are the perfect squares. I'll write that a little bit further above. Okay, and just to show the opposite relationship in a list, we can say that the square root of 1 is 1. So it's kind of like we're going backwards from the first column. The square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. The square root of 25 is 5. Square root of 36 is 6. Square root of 49 is 7. The square root of 64 is equal to 8. Square root of 81 is equal to 9. And the square root of 100 is equal to 10. So this is just showing going forward and backward of squaring and then using its inverse, square rooting. And if you notice, all of the numbers underneath the radicals in this column, all of those numbers are rational. And the reason why they're rational is because they produce numbers that are whole. Sorry about that. Okay, so if you produce numbers that are whole, that means you can write it as a fraction, like 1 is equal to 1 over 1. 2 is equal to 2 over 1. So these are ratios or fractions. So this is just showing that if you square root a perfect square, the product is a rational number. Okay, so that's the example that they give here. 81 is equal to 9 squared, so 81 is a perfect square. That would mean that 9 is a rational number, and so is the square root of 81. So to further this point, a number a is a square root of a number b if a squared equals b. For any whole number b that is not a perfect square, the square root of b is irrational. So think of all the numbers that are not double numbers. Okay, so of that list that we just made on the previous page, all of these right here, okay, those are all perfect squares. If you square root any number that is not in that list, it is going to be irrational. Okay, that's really all you have to remember here. Like the number 90, that is not one of the perfect squares that we wrote down on the list. Because 90 is not a perfect square, when we square root it, the result is irrational. So let's try the first example. It says determine if each square root is rational or irrational. So again, I'm just going to, at the top, remind myself what the list of the first 10 perfect squares are, which was 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Okay, those are the first 10 perfect squares. There are more perfect squares, but we only need to really memorize the first 10. So if any of the numbers underneath these square root symbols are not in this list of perfect squares, then the number should be irrational. So the square root of 4, okay? If I were to think about what number can I multiply by itself to get to 4, that's 2, which is why 4 is in our list of perfect squares. So we would say that the square root of 4 is rational. Okay, it's rational because since the square root of 4 is 2, and 2 can be written as 2 over 1 as a ratio, then it is rational. Now the square root of 6, I cannot find a number that I can multiply by itself to get to 6. 3 plus 3 is 6, but I want to know what times itself would equal 6. Now 6 is nowhere on my list of perfect squares, so I would say that the square root of 6 is irrational. Same thing with the square root of 5. It's not on my perfect square list. Same thing with square root of 7. Square root of 3. Now the square root of 9, okay, 3 times itself, 3 is 9. So the square root of 9 is equal to 3, which we can write as 3 over 1, which is a ratio, which makes it rational. So the square root of 9 is in the rational list. Square root of 8 is not a part of our perfect square list, and same thing with square root of 2. So let's have you give this a try in your first U-try. It says, which numbers are irrational? Think about your first 10 perfect squares, and think also if you can generate more perfect squares beyond just 10 squared. Like, what is 11 squared? What is 12 squared? 13 squared? And see if maybe you can reach up to somewhere around 125 and distinguish if that is a rational or irrational number. All right, so just to introduce you to rational versus irrational numbers as a form of known symbolic numbers and just recognizing patterns, I have that rational numbers are decimal expansions that terminate in zeros. Okay, they terminate in zeros. We talked about that, the terminating decimal, or eventually repeat. Those are rational. Okay, we have to be able to memorize that rational decimals, okay, we can identify if they are rational, if they terminate, if they repeat. That is rational. Irrational numbers cannot be represented as terminating or repeating decimals. So for example, the square root of 10, if you were to type that in your calculator, you get 3.1622766. There's no pattern that I see here. Okay, eventually if I were to keep estimating what the decimal expansion is for the square root of 10, there would never be an end in number. It would go on forever randomly without any sort of pattern. Same thing if you were to see something that looks like a pattern, something cool, but it's not really a repeating pattern. I'm looking specifically for a repeating pattern for it to be rational. Okay, whereas here, even though it looks like, okay, I know what the pattern is going to be. If I were to continue writing out numbers, I see 1 0, then 1 0 0, so it's like a 1 and then 1 0, a 1 and then 2 zeros, a 1 and then 3 zeros. So I would imagine it'd be a 1 and then 4 zeros, a 1 and then 5 zeros, okay, and so on with that pattern. Okay, but just because I can guess what the pattern is going to be doesn't mean the same numbers are being repeated every time, and it's got to be the same numbers in order for it to be rational. So technically, while this pattern is cool, it is irrational. So anything that doesn't repeat goes on forever, or you see like a cool pattern, but it's not a repeating pattern, that's going to be an irrational number. Numbers like pi, okay, that we use in formulas for area of a circle, that is derived by taking the square root of a specific non-perfect digit, which results in an infinite amount of numbers. Most of us know it as 3.14, but that's just the rounded version. And even the number that I have on the screen right now is not even all the infinite amount of digits that go into the number pi. So one thing we can take away from this is a very well-known number represented with a symbol pi is an irrational number. Okay, it is irrational because it is taken by taking the square root of a non-perfect square. In this example, it says determine if each number is irrational or rational. Assume each pattern continues. Now, A is a terminating decimal. It ends. It does not go on forever and ever. There are two types of decimals that create rational numbers: terminating and repeating. If we do not see the decimal terminate or repeat the same number or numbers over and over again, it would be considered irrational. Since A terminates, that means A would be rational. For part B, I see that the 1 is repeating, and it's just the number 1 that is repeating, and it's the same digit that repeats, so that would also be rational. Sorry, I should write it like I did before. This I classified as repeating, which makes it rational. Now, C is that cool pattern that I was talking about, but it's not the same digits that are repeating every time. Okay, so it looks like I have 0, 1, then I have another 0, 1, but then it goes 1, 0. So it's not the same two digits that are repeating every time. Then I have 1, 1. Then I have 1, 0, 1, 1, 1, 1. Not the same two digits repeating every time. So this one would be irrational. Now in part D, I see 1, 2, 3, 4, but then a 1 again, a 2 again, a 3 again, a 4 again, and in the same order. So it's like that 1, 2, 3, 4 is repeating itself. Since that is repeating, that is rational. And then for part E, it does say in the definition of rational for the repeating decimals that it just has to eventually repeat. So even though the 8 and the 0 do not repeat, the 3 eventually starts repeating. So I can actually write this as 1.803 with the repeating bar just over the 3. Okay, if it eventually repeats, that is rational. Let's have you give this a try. Identify which number is not irrational. Not irrational. Okay, if something is not irrational, that should tell you they want you to identify which number is rational. Okay, remember, rational and irrational are opposites. So we're identifying which ones are not irrational or rational. Okay, so I have one more key idea for you here in this lesson, and that's just how to classify certain numbers. Now, each of these number categories are like sitting inside of each other. So all of the numbers that we're going to be talking about are going to be real. Okay, so when you classify any numbers in 8th grade, the first thing you can call them is real. Then you need to decide if they're rational or irrational. In the rational number realm, those are all the numbers that can be changed into fractions or can be changed into ratios. Now, inside of the rational number realm, we have integers. Integers are all of those positive and negative whole numbers, which bring us to the whole numbers. Whole numbers are just numbers that are, like it sounds, whole. There's not pieces of them anywhere. It's not like 1.5, it's just one whole or two wholes, things like that. And then the natural numbers, I like to begin with describing things as we start with the natural numbers, like how we count. When you first are taught how to count, okay, little baby, okay, you're teaching your baby how to count. And they say, when they first start counting, they say 1, 2, 3, 4, and they go on counting like that. Now, that's what makes it natural. You don't tell your baby to start at 0. That would be weird. Okay, so we start by calling the natural numbers like how we learn to count. Okay, how we learn to count. Then from there, we're just adding on numbers, creating new categories. The only difference between the whole numbers and the natural numbers is 0. That's it. There's only one number added on to classify it as whole, and that's 0. Then you're adding on all the negative numbers to create all the integers, and then you're adding on all the parts of numbers to create rational numbers. Notice how rational numbers and irrational numbers are their own two separate entities inside of the real numbers. There is no such thing as a number that can be both rational and irrational because they are opposites of each other. And remember, we obtain irrational numbers by taking the square root of non-perfect squares. Okay, square root of non-perfect squares. Okay, all other numbers you should be able to change into a fraction. So if I were to talk about the number 7 and talk about all of its classifications, I could say that the number 7 is natural. Since natural numbers are a part of the whole number category, it is also whole. Whole numbers are a part of the integer category, so 7 is an integer. Integers are a part of the rational category, so 7 is also rational, and then everything is a part of the real numbers. So we can call the number 7 natural, whole, integer, rational, and real. Now, if I were to just talk about the number -3, that one would not be whole or natural because whole and natural do not include negative numbers. So I could call -3 integers, rational, and real. So let's do this example where we classify a couple of different numbers and they can be in multiple categories. So the first thing I'm going to do is indicate what the number 15 is. 15 is definitely a natural number. When we count, when we start counting 0, 1, 2, 3, 4, on and on, we reach 15. Now, if we look at our chart, the natural numbers are a part of the whole numbers, are a part of the integers, are a part of the rational numbers, are a part of the real numbers. So this is natural, whole, integer, rational, and real. Now, as for this number, -1.232, not only is that a decimal, it's a terminating decimal, and it's negative. So we've got part of a number, and we've also got a negative. You're not going to teach your child to count to this number, so it's not going to be natural. It's obviously not whole because we don't have a full number. It's just part of a number. This would be an integer if it was a whole number, but again, since it's a decimal, it's not an integer either. But this definitely is a rational number. Okay, rational numbers are any numbers that can be put as a fraction. And then all of our numbers that we're going to be talking about are real. So the number -1.232 is just rational and real. The square root of 45. Now, 45 is not a perfect square. The two perfect squares that surround 45 are 36 and 49. Since 36 is 6 times 6 and 49 is 7 times 7, 45 is somewhere in between 6 and 7. So it is a non-perfect square. Taking the square root of that would result in an irrational number. If it's irrational, it cannot be any of the top four, but it definitely is a real number. All of our numbers are real. Now, looking at this number, it's already in fraction form. So I can tell that that is a rational number. Now, I don't see if it's an integer or not. I can try to simplify the number 121 over 35, but I'm not seeing a number that I can divide both 121 and 35 by. 121 is divisible by 11, 35 is divisible by 7. I'm not really seeing a number that either of these are divisible by, so I'm not sure I'm going to get a whole number out of this. So I just think that this is rational, and if it's rational, it's also real. Can't be irrational. The next one, negative square root of 16. If we simplified that, the square root of 16 is 4, so that would just be negative 4, which can be written as a fraction, negative 4 over 1, which is rational. Negative 4 is an integer because it's a whole negative. It is not a whole number, though, because by definition, whole numbers do not include negatives. And it's not natural because, again, we don't teach our child to count in the negative area. But all of our numbers are going to be real. Last fraction here, I can definitely tell that this can reduce. 21 divided by 3 is 7. 7 is a whole number that can be written as a fraction. So that's rational, integer, whole, and it definitely is natural. We naturally count to 7, and which would make that also real. So we went over a bunch of different examples of these numbers and what name categories they can be in. I want you to try to classify all the names for 1 and 2/9. All right, I have 3 last questions I want you to answer in your close-in check to see if you really truly were listening and if you really truly understand what all the new vocabulary means as far as square roots, square, perfect square, rational, irrational, terminating, and repeating decimal. So answer these questions to the best of your ability. Make sure you ask any questions if you are confused. All right, so that pretty much wraps up our lesson on classifying numbers as rational or irrational. We identified types of decimals. That was in example 1 and in the key concept. We identified a fraction or a ratio from different numbers. We did that in examples 1 through 3. And then we were able to distinguish a number between rational and irrational on examples 2 and in example 3 with those number families. So go ahead and start your Google form. Make sure you ask any questions or go back and rewatch any sections that you did not understand. Thank you and have a great day.